Hello, this is Jiang from Texas A&M University. I'm glad to present our work on transaction-level stimulus optimization in functional verification using machine learning predictors. This is the outline of this presentation. At the beginning, I will show the challenge of functional verification, and then I will introduce the background of this work. After that, I will describe the main machine learning techniques for functional verification, and at the end, I will give the conclusions. Functional verification is mostly realized through simulations. That is to provide input stimulus to an RTL design and then analyze the output response to see whether or not it is the same as the correct answer. So if we look at the design cycle in this chart, horizontal axis is the time in terms of weeks, and the vertical axis is for the coverage. At the beginning, the coverage is low. It takes a long time to reach a high coverage. The reason is that the design space is huge, so it takes a long time to cover the whole space or the majority of the space. And in this simulation-based verification, the simulation takes a lot of time. So nowadays, verification takes a lot of designers' time and manpower, and actually it costs more than design time and then the manpower spent for chip design. So now let's look at the stimulus in the typical verification flow in a UVM environment. There are three hierarchical levels. The top level is a test. So let's consider a case for multi-core design, and a test is composed by multiple sequences. And one sequence is composed by multiple transactions. These are randomly generated or by directed random generation from a UVM environment. In this UVM environment, there are some constraints for those test level generation. We call them test knobs. For coverage, there are different metrics. And here in this work, we focus on the functional coverage. And there are different ways to evaluate the coverage. One is cover point. One is that is for a specific functions. For the whole space of a cover point, it can be divided to multiple 0-1 binary bins. And related cover points can form a cover group. The machine learning is to push this coverage curve toward the left so we can reduce the verification time and achieve high coverage in a shorter time. So how to do that? We build a machine learning model. The machine learning model is to tell whether or not a stimulus will cover a new point which has not been verified in the previous test. Then we simulate this stimulus only when the answer is yes. So if the answer is no, we will prune this stimulus from simulation because it won't improve the coverage. So this by doing this pruning, we can save the verification time. There are many existing machine learning works. The questions is, are these existing works sufficient? The answer is no. First of all, many of these works are based on old machine learning techniques, for example, SVM. And at the same time, there are many new machine learning techniques that have not been well studied yet for functional verification. And also, let's look at the granularity of the application of a machine learning model. Previous work are mostly restricted to test-level coarse-grained designs, and there's almost no previous work looking at transaction-level or fine-grained designs. And also, there are two different ways to consider the stimulus. One is a passive pruning by a machine learning model. The other way is to construct those stimulus using machine learning model. Also, there could be finite submission design, transition coverage, and a non-finite submission design. These issues have not been well studied yet. So now let's first look at the conventional test-level machine learning assisted functional verification. That is, at the beginning of the verification phase, we do random test as usual. At this moment, we build a machine learning model. To a certain point, typically this bend or knee point, we started to apply this machine learning model and then try to prune out those stimulus which do not help to improve the coverage. Then we can reduce the simulation time. And in this phase, besides applying this machine learning model for pruning, we can continue to train this model. So here's the setup. Okay, we have like one machine learning model for each cover point. A group has multiple points, so we have multiple models. And for each model, we have multiple outputs, each corresponded to one bin. And we can tell from each output to see whether or not a bin is covered or not. And these are some examples of features. These features are the test knobs in the UVM environment. This is one example of design under test, which is a 4-core processor design. And these are some examples of cover points. Traditionally, the classification is mostly binary. We tell a stimulus will improve the coverage, yes or no. Now, we'll suggest a ternary classification. That is, besides yes and no, we have a middle category. So that is to say, we look at the probability for improving the coverage by a test stimulus. If it is high enough, the answer is yes, we simulated that. And if that's not, then we do not simulate. If it is in the middle case, actually, we still simulated. And at the same time, we'll apply this simulation result to continuously train the machine learning model. Now let's look at the result of this test level application of a machine learning model for one group. For this particular group, those test knobs are well correlated with the coverage metrics. So the effect of machine learning is very significant. The horizontal axis is the number of tests, and the vertical axis is the coverage. So we can see that without machine learning, it takes a long time to have high coverage. By using machine learning, we can reach high coverage in a much shorter time. And among these different machine learning models, random forest result is the best. We also compare binary classification and ternary. So the blue bar are from those without machine learning, and then the other three are from machine learning. So we can tell that the ternary classification can further reduce the number of simulations. However, for this coarse-grained test level application of machine learning, it won't work for some cases. So this is another group, group B. For this group, we can tell whether or not to apply machine learning. The difference is very small, because for those cases, those test knobs, they have a poor correlation with those test metrics. So that means this coarse-grained level test level pruning is not sufficient. And then we study 4 combinations of for this of a different fine-grained control of application of a machine learning model. These four combinations include online pruning and offline sequence generation, and also finite state machine design and non-finite state machine design. So let's look at finite state machine design. We look at state transitions. This framework is similar as the previous one, but we apply it as transaction level, which is finer grade. And also we consider to construct the sequence instead of do this passive pruning. And the way to generate the sequence is to construct a graph. This graph is similar as a state transition diagram for the finite state machine, where each node is a state and each edge represents a transition. And for the transition that has already been visited in previous tests, we give a low weight. And for those edges who has not been visited in the past, we give a high weight. And then the problem is to find a longest path from the initial state to the illegal state. So for example, this green path is longer. So by using this sequence, we can improve coverage more because we can touch more edges who have not been covered in the past. And we compare this online pruning and offline pruning. Online pruning, it has only near-term effect, which is not good. And the offline sequence, we can look at a long-term effect. So now let's look at the result on messy cache coherence protocol. And there are 143 bins. And here we use deep neural network as the main machine learning engine. We compare this no machine learning. And this one is the test level optimization. We can see it is not effective. By using transaction level application of machine learning model, we can reduce these simulations a lot. And here, this is this one directed sequence get a better result than this pruning. And this result is from random forest. We can see similar trend. So now let's look at the overall time. So this part is the simulation time, this is model training time, and the model prediction time. So we put all of them together, we can still see a significant reduction. So this directed sequence generation, we can reduce this runtime, the overall verification time, by near like 70%. So now let's look at the non-finite state machine design. In this case, we look at event coverage. Event means like a buffer full or cache hit. And this case, whether or not, it will bring new coverage, it highly depends on the history. And the original method won't work well. So now let's look at the history effect. And we look at the two different models, random forest and LSTM. And the horizontal axis is the history window size we look at. 0 means we don't look at any history. This is we look at the history of one transaction in the past, 2 transactions past, 3 transactions past. So the vertical axis are the model error. So we can see that by including a history of about like 10 transactions, we can reduce this model error. And also LSTM performs better than random forest. So now let's look at the result of this non-finite state machine design event coverage. And for this case, we look at over 700 bins. And again, if we look at this coarse-grained test level pruning, it does not make much difference from the case without machine learning. And if we do this transaction level optimization, we can reduce this simulation a lot. And between these two approaches, this direct sequence generation is better than the online transaction pruning. And here again, this is the overall result. And so this is simulation time, machine learning model training time, and machine learning model predicted time. And overall, we can reduce the total verification time by 72%. So here are the conclusions. We can see that machine learning model indeed help accelerate the functional verification. We also show that it is important to consider fine-grained transaction level optimization because in some cases, they significantly outperform coarse-grained test level pruning. We also show that offline sequence generation is superior to online stimulus pruning. And our experiment results show that by applying our proposed machine learning techniques, we can reduce the overall verification time by about 70%. That's all for this presentation, and thank you for your attention. If you have any questions, feel free to contact me, and this is my email address. Thank you. Bye.